started recording again. Okay, totally bummed about that. All right. Whew. So I get a B- for technology today. All right. So you guys, back to this problem. I think this was the substance. Okay. All right. So you guys, we added water. Is everything okay? I'm just looking at the chat to make sure, because with the tech adjustment, are we back in this? You guys can hear me again. You can see the screen. All is good. Oh, you guys are so sweet. Thank you. Okay, so hopefully adding the water is clear. Okay. When you add water, you guys want to know the truth of it? The truth of it is when a stress, like adding water, when it changes both ion concentrations, okay, it's affecting the silver ions and the carbonate ions both. When that happens, guess what? They go back to normal. Okay, so there's not going to be any change. They're just going to go back up to what they're supposed to be. Okay, so the shift was forward, mass of the precipitate went down. Okay, but watch what happens this time. Okay, and I apologize, these are in a slightly different order. So what if you add acid? Now, you guys, HNO3 tends to be my go-to acid, but realize, I could say it differently. I could say, what would happen to the solubility if this was in a low pH or something like that? Or I could use a different acid. I tend not to use HCl because the chloride causes problems with precipitates. So HNO3 tends to be the best acid because it doesn't make any precipitates with anything, okay? But adding HNO3 just basically means you're lowering the pH. Okay, so when you add HNO3, what kind of salts are more soluble in the presence of acid? Okay, and I hope you guys are just yelling at your screen that basically you want to look for OH minus, if that's part of the salt, or conjugate bases of weak acids. Okay, those two particular anions, they're going to be more soluble in acidic conditions. Okay? So when I look at carbonate, I say, yep, that's a winner. Okay, so carbonate is a conjugate base with weak acid, so that H plus would bind with that carbonate, okay, and that would make HCO3 minus. So that would lower the carbonate, so which way would the equilibrium shift? Okay, it would shift forward because we're going to have to replenish that carbonate. What would happen to the mass of precipitate? Since we're shifting away from the precipitate, that's going to lower the mass of the precipitate. Mass of precipitate. What would happen to the silver ions? Okay, well, we're shifting towards the silver ions, so they're going to go up because by adding that H plus, at low pH, the carbonate went down. So that's what I mean. In this case, you're messing with one of the ions, so the other ion has to compensate. So when the carbonate went down, the Ag plus has to go up so that when you multiply those in the KSP expression, you get the same exact number. Does that make sense to you guys? Okay, so that's the big difference. But when you change both ions proportionally, then they're both affected the same way. They just go back up to where they originally were. Okay, so let's see. Can't remember the next one on the list. I probably added, I'm guessing maybe some solid, maybe sodium carbonate. Does that sound good? Okay. And I really wanted to specifically use the word solid because you guys immediately turn off when you see the word solid. You're like, oh, solids don't shift to equilibrium. But keep in mind that alkali metals and nitrates, I think those are the big ones. As soon as they hit the aqueous media, they're going to break up. So really, sodium carbonate is really sodium ions and carbonate ions. Okay. So that being said, whoops. That being said, oh boy, I got some screens popping up, sorry. That's common ion effect. So that's basically increasing the carbonate. So which way are we going to shift? Okay, we're going to shift backwards. Okay, because we got this common ion present. What's going to happen to the amount of precipitate? We're shifting towards the precipitate now, so it's going to get heavier. And then again, with your ions, okay, so the carbonate ion concentration is going up. Now you are shifting away from it. Okay, so it is going to come down a little bit. Okay, but since this guy is going down as well, the net change is it's still going to be higher than it was. Okay, so that's another really great point that happens with equilibrium. Okay, so again, since this guy went up, this guy is going to be down in order to compensate. Okay, so when I multiply these guys in the KSP expression, it comes out to the same number. Okay, and then somebody asked a great question while we're looking at this one, said, well, we have to figure out what both H plus and CO minus will both do in a solution? And the answer to that is no. Okay, like that's too complicated. I wouldn't know the answer either, because if we used HCl instead of HNO3, that Cl would hook up with the Ag plus and you'd get this other precipitate. So actually, I guess that's not that bad of a question. Someone said if you used HCl as your acid as well, or instead, of course, the H would lower the concentration of the carbonate, okay, because it's a conjugate base of a weak acid. And the Cl minus would hook up with some of the Ag plus and would lower that. So I guess it would lower both ion concentrations, which would just increase the solubility of the precipitate that much more. I think what's confusing about that is the Cl minus would be like a precipitate replacing a precipitate, and that gets kind of ugly because you probably wouldn't be able to tell that this guy was becoming more soluble. So I think that's where the confusion is. Okay, we don't really want to have to deal with two precipitates at the same time. Okay, so great question though. All right, let's see. And I know I had something else on the list. Let me think here. Oh, it might have been I added something. Oh, NH3. Okay, you guys are so good. Thank you. So if we added NH3, well, you guys, I hope that I triggered you to think complex ions, okay? Because again, that's what would happen here. And I think I even said excess. Okay, that again, Ag plus is one of those metals that likes to make complex ions. Okay, so the Ag plus would hook up with NH3, okay, and that would lower that, so it would shift forward. Okay, again, since you're shifting away from the precipitate, the mass of the precipitate would go down. Okay, and then as you shift forward, of course, the Ag plus went down. Again, it's going to come up a little bit when you shift forward, but it's not going to go up to where it originally was because the carbonate is definitely going up. Okay, so again, you guys are noticing a trend that when you mess with one ion, the other ion has to compensate, so they're always opposite. Okay, I think another one that I added here, I'll have to start erasing here, was thank you, okay, for reminding me. So we're good with this one. I'll just go and erase it. I said, what if you added solid? Blue here. If you add solid, Ag2CO3. So that's kind of a silly question in this light, but I wanted to throw it out there anyway, because that is the precipitate, right? So it's a saturated solution. Remember how we said that? So if you add more silver carbonate, guess what? You know what? It's already a saturated solution. So no shift will occur. Okay, there's not going to be a shift. And of course, the ion concentrations are going to stay the same. Okay, and you know what? Obviously, yes, you're going to make more precipitate because all that solid Ag2CO3 is just going to add to the precipitate that was already there. Okay, and I think I added one more at the bottom, kind of another one to really throw you guys off, which was, get rid of that, sodium nitrate. I think that was right. Yep, and someone backed me up on that. Thank you. Okay, so what if you add some solid sodium nitrate? So again, I wanted you guys to remember that, just because it's solid, that doesn't mean it's solid. Okay, sodium nitrate, an alkali metal and nitrate, that as soon as it hits the aqueous media, it's going to split up. So I'm basically adding sodium ions and nitrate ions. And I say to myself, gosh, is sodium going to interact with anything? Not really. Is nitrate going to act with anything? It's like spectator sandwich or something. So to be honest, that's not going to have any effect on anything. It would just dissolve. Okay, it would just dissolve and be hanging out with all the other ions that are there. Would not do anything. And I guess while we're at it, I am going to add one more. Why not? A little blast from the past for you guys. Make a little space here. What if you increase the temperature? Okay, so increase the temp. Whoops, I'm going to try to get that on there. Increase the temp. So guess what? I will tell you, based on the information I gave you right now, you should say, I don't know. It could go either way. Okay, because what critical piece of information do you need to know if temperature is going to cause the reaction to shift forward or shift backwards? And it does not matter if it's KSP or weak acid equilibrium or gaseous equilibrium or any equilibrium. It does not matter. K is the same in this regard. okay, you would have to know, I hope you guys are like saying it out loud, you would have to know if it's exo or endothermic, okay? So I'm just gonna go out on a limb here and I'm gonna say delta H for this reaction as written. We'll say it's a negative 10 kilojoules. Okay, so that negative implies exo or endo. Okay, so that means it's an exothermic process. So our energy quantity would be on this side. Okay, so of course endo would be on the reactant side. Okay, so if I increase the temp, that means we're going to add energy. So that's going to cause the equilibrium to shift backwards. Okay, if it's exothermic, we're adding energy, so you're going to have to shift to get rid of that energy. You're going to have to shift backwards. Okay, so it would shift backwards. Precipitate's going to increase because we're shifting towards a precipitate. And of course, we're shifting backwards. So what's going to happen to both of these ion concentrations? They're both going to go down. Okay, and that's totally acceptable because also what's going to happen to KSP? If you shift backwards, K goes down. It becomes less favorable. Okay, if you shift forwards, K goes up. So if you're producing less silver ions and less carbonate ions, that means when you multiply them in KSP, K will go down. Okay, so just remember I think there's one question on the assessment that reminds you of that. Okay, that temperature is the only factor that changes K. Okay, and you gotta look through the problem and figure out if it's exo or endothermic. Okay, all right, I hope that helps. Okay, so I'm going to catch up on the chat. We were getting ready to talk about number 23, so I will go back to that. I'm going to leave this up here for 1 second, though, before I change the screen. Does anyone want to yell out a number? Ah, I see. Yes, someone yelled out endo versus exo. I love it. Okay. Looks like I'm not seeing any new entries into the chat about this question, which is great. Okay, so you guys asked about number 3 on page 23. I like this question quite a bit. Okay, so it said, so you have this lead iodide, right? Okay, and it says 200 mils of a saturated lead iodide solution is evaporated to dryness. Calculate the KSP for the substance if 0.12 grams of it were recovered after evaporation. First of all, you guys, that's just an interesting question. Like, just remember when you have a precipitate, let's say that's the dots are my lead iodide, okay? If you filter, you got 2 ways you can collect the precipitate, okay? One way is you could filter it, right? So if you filtered it, all the precipitate would collect. You could dry it, you could mass it, okay? Or another way is you could evaporate all the water, okay? And then the only thing that would be left, okay, would be the precipitate, okay? The lead iodide. So that's 2 different ways you can actually collect it. So in this case, we got rid of all the water. So you had 0.12 grams of lead iodide, okay? So of course, first, that's really the molar side, not molar, that's the gram solubility. That's how much of that solid actually dissolved in water. So you definitely want to go ahead and convert that to moles. Let's see, the molar mass of lead. Okay, let me look that up real quick. Okay, let's see, I'm guessing around 460, 461-ish. Does that sound good? Okay, so that's lead iodide. Okay, so that's your that would get you moles of the lead iodide that dissolved. Okay, so I think that comes out to about typing it in my calculator 2.6 times 10 to the negative 4th. Okay, and that's moles of lead iodide. And you guys, you know what? Pro tip right here. Don't forget that everything has to be in concentration. So that's fine that I have the moles. Okay, but I have to remember to divide that by what the total volume was. Okay, and it said 200 mils of saturated lead solution. Okay, just remember also the word saturated means that that system was at equilibrium. Okay, so put it over this many liters. Okay, so that means that the concentration, okay, it came out to about 1.3 times 10 to the negative 3rd. Okay, now that is the molar solubility. So that's basically your X value in an ice table. Okay, that's how much of the lead iodide actually dissolved to make a saturated solution at equilibrium. Okay, and then it's just a matter of asking this question. Is this a case where the ions came from the same source, or did the lead and the iodide come from different sources? Okay, and I hope given sort of the nature of the question where you had lead iodide and you just got rid of the water, that the lead and the iodide came from the same source. So what that means is that this is a time where the lead and the iodine have to be in a 1-to-2 ratio. Okay, so if this is lead iodide, there's 1 lead for every lead iodide, so that would be equal to the lead. And then if you want the iodide, it would just have to be this number doubled. Okay, because there's 2 moles of I per every lead iodide. Okay, so you would double it. Okay, so that's about what, 2.6 times 10 to the -3rd molar. Okay, so there's your 2 numbers. Okay, so you have the concentration of lead, you have the concentration of iodide. Concentration of iodide is double that of the lead. So now you guys can put that in the KSP. Okay, so bing, bam, boom. This guy's good to go. This guy, of course, because it's got the 2, we're going to have to square it as well. Okay, so I'm pretty darn sure that will probably get you the correct answer, which I believe is E. Okay, so I'm going to look at the chat to see if there's any further questions about this problem. So I'm going to look up. Yep, just asked. All right. So question says, so here we assume there was no excess solid. That's right. So in the language, it said that 200 mils of a saturated lead iodide solution. So that, it didn't say anything about having any extra precipitate. So if there was precipitate, that just means that they'd gotten rid of it. Okay. Like I said, so they, you know, they might have filtered off if there's extra. So you just had the ions left. Okay. Yep. Okay. So any other questions? Somebody asked for the calculation, putting the value into 4x cubed would absolutely work. Yes. So that's a great point. So once you concluded that this was x, let me use a different color. Once you concluded that this was your x value right here, absolutely. You guys, this would be an appropriate time to do 4x cubed. Okay, so yes, you can do that. Just remember sometimes I think at this point, you guys, you know, you really know what you're talking about. So you get so used to using 4x cubed that you kind of forget where it came from. Okay, and it did come from, you know, like literally PB2 plus I minus squared, you know, and this was x, this was 2x, and you had to square it. Like you had to actually do that algebra. Okay, so as long as you just kind of remember that that's where it came from, then yes, totally awesome. All right, other questions about that one? Okay, and actually now that I think about it, I think I can see someone asked a really great question, and I think my picture right here probably wasn't the most clear, so I'm going to make that a little clear. You know, talking about solutions and precipitate, so I'm going to make it a little better. So, you know, this problem, what it would have looked like is a saturated solution of lead iodide. Okay, it would have looked like this. Okay, and notice there's 2 pp. There's the ratio, okay, of 2 I minuses to every PB. So if you guys agree with the ratio, so that's what, this is what the saturated PbI2 solution would look like. Okay, perfectly saturated. Okay, then once you got rid of the water, so this is like what it looked like originally. Then once you let the water evaporate, what happened is, you know, as the water left, that lead iodide wasn't able to stay dissolved, So then what you had left at the bottom was just PbI2. Okay, so like as precipitate, as solid. Okay, and then everything else is empty. So that's what that would look like. And then when you mass this, that weighed 0.12 grams. You guys see? Okay, so I think that's a clear picture. So I think someone asked a question that kind of got me thinking, oh, okay, that's probably a better way of showing that. Okay. All right, I'm going to take a breather. I'm going to go back up to the top. How are you guys doing? All right. How are you guys doing? Are you guys worried about this test? This twiz. It's a twiz. Okay, I hope not. I think the twiz is pretty straightforward. I hope you guys feel that way. It does have some interesting questions though. Okay, so make sure and read it real carefully. But you guys know, when I think it's an interesting question, it usually is kind of wordy and convoluted and has a weird context, but at its core, it's probably not that hard. Okay, so make sure you just kind of whittle through it to see if you can find where the chemistry lurks. Okay, let's see. All right, so I'm going back up to the top. It says, how do we know when to use the mole ratio as coefficients and to the power of? An example would be page 24, question 15. Okay, page 24, question 15. Okay, that's a great question. Let's see, I'm gonna open up a new page. So page 24, number 15, it's kind of a tricky question. So it says the solubility product expression for this really weird precipitate. Okay, so this was my solid, my precipitate. Okay, and just remember, like, go back to the basics. When you write KSP, it's going to be whatever the TB is. Okay, whoops, I guess that's a 4 plus. And it's going to be raised to the third power. So like this is non-negotiable. Okay, for equilibrium, whatever that subscript is, you're going to raise it to that power. And then the phosphate has a 3 minus charge, and you're going to raise it to the 4th power. Okay, so I think that would be choice A, because that's how you write a KSP expression. Okay, but if you broke that down into X, just remember that this is the KSP expression. But if you actually want to solve for something, then it looks a little different. Like if you set up an ice table, okay, this would actually be 3x cubed, and then this would be 4x to the 4th, right? So then all of a sudden you bring those in, but just remember, like x itself, okay, is going to be like if x was 0.001, okay, then 3x would be 0.003, right? Okay, well, when it just says TB4 plus, they've already taken into account the fact that it's 3 times that. Okay, so it almost, if you're having trouble with understanding number 15, it's just like, are you putting it in terms of x? Then it has to be 3x, because x is like sort of the bare minimum, like brought down to 1. Or is it in terms of the variable? Okay, like TB, in other words, is equivalent to 3x. So I think that's kind of the designation. Okay, so that's why A is the best answer, and C is just not right. It would be right if they wrote 3x cubed and 4x to the 4th. Okay, do you see my point? Okay, so that's all I can say about that. I know it's kind of a weird question, but that's really all there is to it. Whether you're using X or whether you're actually, what the substance actually is. Okay, so I'll leave it at that. It's a great question, a little confusing. You could see why you asked about it. Okay, so I did number 3. Can we go over question 1 and 5 on page 23? Absolutely. Okay, so I'm gonna skip ahead here. Oh, I do love number 1. Okay, and I kind of feel like, I think I kind of went over number 1. It sort of went over it already with things that affect Le Chatelier's principle. Okay, but I'll go over it again real quick. Okay, so for number 1, okay, it just asked what factors would increase the solubility. So it's basically which ones would cause a shift in the forward direction. Okay, and of course, the answers are 1 and 3. Addition of NH3, like we talked about just a minute ago, that's going to do the complex ion formation. Okay, so that's going to cause the silver ions to go down because the Ag plus is going to bind with the NH3 complex ion formation. It's going to make it shift forward. Okay, so complex ion formation is a factor that's going to make precipitates go away. It's going to increase the solubility of a precipitate. 2, of course, is opposite because it's common ion, so you're increasing the carbonate, so it'd shift the opposite way. And then, of course, the HNO3 is that acid, so carbonate being a conjugate base of a weak acid will be more soluble, okay, in the presence of that acid. Okay, so that would do the opposite. That would decrease this. Okay. Whoops. And cause this reaction to shift forward. Okay. So, yep, I think that one's pretty good. There we go. Okay, and then somebody asked about number 5. Okay, number 5 on page 23. It's a fun one. It's sort of like a domino effect. Okay, and I'll just give you guys a hint about it. It is pretty fun. You got this first reaction is a great example of complex ion formation. You got your nickel. You guys remember what metals do complex ion formation? I call them late transition metals. Okay, so if you're looking at your periodic table, like copper and silver are the big ones. Okay, but any metals in that region. Okay, so cadmium's over there, nickel's over there, even aluminum. Okay, gold. Those guys, they will undergo complex ion formation. And NH3 loves to do complex ion formation. I know it's the only example I've used today, but if you use Cl minus, it's going to do the same thing. Cn minus would do the same thing. So any of the halogens, okay, are going to do the exact same thing. And OH minus is another one. So you guys remember we talked about like these things that connect the metals. What they all have in common is they have negative charges or they have like extra lone pairs. Okay. Remember these guys are called Lewis bases. And a Lewis base by definition is just something that donates a lone pair. So that would be that lone pair on the nitrogen. And these guys all have various lone pairs too. Okay, and that makes the nickel 2+, the Lewis acid, because it's got that positive charge, so it has the ability to accept the lone pair. Okay, so you guys know I'm not going to ask like real nitpicky definition stuff. You guys probably wish I would. Okay, but that's some of the behind the scenes concepts there. Going back to this problem, we got then this reaction, which is just basically your weak base dissociating. Okay, and then last but not least, okay, we're making a precipitate. Okay, got aluminum plus OH minus making aluminum hydroxide. Okay, so bottom line is, addition of more aluminum ions. Okay, so it all starts with the aluminum ions. Okay, and it's just Al plus 3 all by itself. So addition of aluminum ions, what would it do? Okay, well, when you add the aluminum ions, it's going to shift this reaction this way. So that's step 1. Okay, and what that does is that lowers the OH minus, so that's step 2. Okay, and when the OH minus gets lowered, that causes this middle equilibrium to shift forward to compensate. Okay, so that's shift 3. Okay, and when that happens, that's going to influence this top reaction. Okay, and that's going to cause that ammonia to go down, which is going to cause this reaction to shift backwards. Now tell me that wasn't pretty cool. Okay, so it all started right here, and it was just like this, the Schefter's dominoes effect. Okay, so this guy went up, and you guys can kind of see if you follow the numbers, how it's just one shift after another. So when it's all said and done, let's see what the outcome is. This guy, we shifted towards it, so it went up. The nickel concentration would go up. Okay, and also the NH4 plus would also go up because in this middle reaction we shifted towards it. Okay, the only one that's not true is increasing this complex ion. This guy right here, it did not go up. It actually went down because we shifted away from it. Okay, so you can see that basically 1 and 2 are true. Okay, so what do you think? Kind of a fun one, right? Okay, so I'm going to look at the chat. Does anyone want to throw out any questions about this one, which is number 5? Okay. Let's see. So I did that one. Oh, I like that one. How does the mass of precipitate go up if the equilibrium is shifting to the right to create more ion? Okay, so someone asked a question. I think it was Shana. She said, let me look. Let's see if I still have that. Let me just look. I feel like somebody's maybe I made a mistake here someplace, but the bottom line is when you guys are shifting, if you shift towards the precipitate, you make more of it. If you shift away from the precipitate, you're getting rid of it. So if I misspoke someplace during the technology mishap, then I apologize. Okay, so I'll just leave it at that because I don't think I have the original one. Okay, for number 4 on page 23, says, does it matter that there are different numbers of ions, or can you just compare the KSP values? That is a great question, and it does matter. So there's actually two things going on with number 4. Oops, I'm not a fan of this yellow. Okay, whoops, try again. So actually so this is back to page 23, number 4. This one's actually a pretty interesting question. It says a solution is prepared such that the concentrations of F minus, Cl minus, Br minus, and sulfate ions, sulfate 2 minus, are 0.001 molar. Okay, so they're kind of set. So what was that? Fluoride. What else we got? Chloride, Br minus, and sulfate. Okay. They've been set to 0.001. And then it says some solid lead nitrate is added to the solution. Okay, now, so lead nitrate, again, you guys don't be fooled. Just because it's solid lead nitrate, it's not really solid. It's basically you're adding lead ions and nitrate ions. Okay, and you guys can probably guess the nitrates are spectators. So you're basically adding these lead ions. Okay, and slowly but surely, the lead ions are going to precipitate with each one of these. Okay, because lead's part of PMS. Okay, so lead loves making precipitates. Okay, so it says which of the following insoluble salts will precipitate first. Okay, so basically what that really means, if you want to solve that, the best way is you need to take each one of those. Like for instance, the first one, lead fluoride. Okay, we're going to set up the KSP expression. So KSP was given as 3.7 times 10 to the negative 8th. Okay, and then I'm looking for the lead ions, but the fluoride ions have already been set to 0.0010. Okay, and I'm going to square it because of the 2. Okay, so the question was asked, can you just look at the KSP values? No. Okay, you really have to actually solve for the lead ion concentration. Okay, so if basically these anions are set for here, we're going to solve for the lead, and we're going to look for the smallest lead value. So for this one, when you solve for the lead 2 plus, it came out to 0.037 molar. Okay, so what that means is that when you're adding that lead dropwise, when it reaches a concentration of 0.037, okay, you've made a saturated solution, like you're at equilibrium. So any concentration, any drops above that, okay, any concentration above 0.037, you're going to see a precipitate. Okay, so you can go through each one of them. Okay, but the correct answer actually works out to be D. So let's look at those numbers. Okay, so that's lead sulfate. Okay, so the KSP is 1.3 times 10 to the negative 8th. Okay, and then for lead, that's what we're looking for. And the sulfate again is 0.001. Okay, so if you do the algebra there and you solve for the lead, for this one, it comes out to 1.3 times 10 to the negative 5th. Okay, so let's take a look at those two numbers. I'll box this one, and we'll just use letter A to compare it to. Okay, you're looking for the smallest one. The smallest lead ion concentration wins because you're adding lead dropwise. So when you reach this much smaller lead concentration, guess what? Any concentration above that, you're going to see a precipitate. So when you go through choices A, B, C, D, whatever, I don't know how many there are, E, okay, whatever lead ion concentration comes out the absolute lowest, that's going to be the first one to precipitate out. Okay, so what do you think of that? So that's a great question. So what I'd want you guys to recognize from this is that this is more or less it's not quite a Q problem, but the ions come from different sources. That's the big idea. You had lead nitrate, that's your lead, and then you had all the other ions, coming from that 0.0010 molar solution. So the big thing is that the lead and whatever the anion is, they're not in their stoichiometric ratios. Okay, but you still, when appropriate, had to take into account the subscripts by squaring it appropriately when you're supposed to. So the squaring still happened when needed. Okay, but you didn't have to double. Not that wouldn't be appropriate there, but you didn't have to double this concentration because there's 2 steps. You know what I mean? Okay, so when the ions come from different sources, they just are what they are. So if these ion concentrations had been set to whatever the problem said, then just use it as is. Okay, so then you just have to say, oh, okay, well, what does the lead ion concentration have to be so that when I multiply them and I calculate KSP, I make a saturated solution. Okay, so what do you think? That's a great question. Okay, that's definitely one you guys might see. Okay, so what questions do we have about that one? So it says number 4, would you need to calculate X or just choose the one with the least KSP? So hopefully that's clarified now. For this one, you did solve for X, right? You had to solve for the lead ion concentration, which is really equivalent to, what the lead ion concentration have to be, okay? So I think I answered that one. Okay, good. All right, let's see. We're going a little over time, but I want to make sure that I get all these questions answered. So then I think God bless somebody who's been, I think, asking the same question a couple of times, and I haven't gotten to it. So I'm going to get to that one first. It's just in general, complex ion formation. What did I see? Okay. I thought I saw something. Oh, it says, how do we write an equation for complex ion formation? So I'll do one of those real quick. So for complex ion formation, let's say, I don't know. Let's say, let's do cadmium 2+. Oops. And we're going to react it with, even better, I'm going to make that one a little more interesting. How about we had cadmium nitrate with excess, okay, sodium chloride, or let's make it sodium iodide. Okay, so, and I would say, oh, okay, so write out the complex ion that would be formed. And folks, complex ions, that's a really small topic. So don't expect those to come out of the blue. Okay, like I would say cadmium nitrate and excess of sodium iodide makes a complex ion. Write out the appropriate net ionic equation. So hopefully you recognize that cadmium is the active player here, and nitrate's just the spectator. Okay, and then sodium iodide. Okay, so sodium's the spectator, and we're just dealing with I-. This guy has a +2 charge, so we're going to double it to see how many iodides connect. Okay, we're going to use the double arrow, and then it's a synthesis reaction. So you're just putting these guys together. So it's going to be I4, okay, and then this whole thing has a charge, and you just kind of got to put the charges together to see what it is. So cadmium's a +2, and I is a minus, but there's 4 of them. So it's a +2 and 4 minuses. So this thing in its entirety would have a -2 charge. Okay, so that big old ion, that's why it's called a complex ion, right? So cadmium with 4 iodines, it'd be like cadmium tetraiodide or something, would have a -2 charge. Okay, and the thing about complex ion formation is they're never precipitates, never, ever, ever. Like their goal in life is that they're aqueous. Okay, they make precipitates go away. So it's going to be aqueous, and whatever the K value, which KF is the appropriate symbol for complex ion formation, is just going to be very large. So much greater than 1. Okay, and that's really all you need to know. Okay, so if you guys can do that, you automatically get a question right on tomorrow's assessment. Okay, what do you think? All right, let's see if we got some other ones real quick. Twiz is no calculation. Will we have numbers like these? Okay, I think the numbers that you'll have on tomorrow's assessment will be pretty user-friendly. They're going to be exactly like the no-calc practice. So if you go back and just practice a few of them, I think that's what you will see. So I think I hit the complex ion formation. Okay. Yeah. So like in terms of like how it would affect solubility, I would say something like this. I would say, let me clean this up a little bit here. I would say, what if you had, like, I don't know why I keep gravitating towards silver compounds today. Actually, I don't even like that one. I can't use that. I will use cadmium sulfate, okay, which actually is a precipitate. Okay, and I would be, oh gosh, how would this equilibrium be affected if I added a bunch of I minus? Whoops. Okay, so I would say, oh, in the presence, okay, of a bunch of I minus, like so solid sodium iodide or something like that. Okay, how would that shift? And I would probably add the word excess. Okay, because that's just kind of a hint that complex ion formation is going to occur. So then hopefully you'd recognize, oh, you know, gosh, cadmium is one of those metals and I minus is one of those anions. Okay, so then cadmium would indeed bind with the I minus. Okay, and the cadmium would go down and that would cause the precipitate to disappear. Okay. All right, so that's probably what you need to know about complex ion formation. And you know, cadmium and iodine, you know, not the most common one. You know, I would just, like I said, copper 2+, Ag+, those are the big ones. These are the ones that love to do complex ion formation, and really with ammonia. Okay, like that's the most common things that you guys see. Okay. How about 10 on page 24? Okay, I would say don't worry about number 10 on page 24. If you're worrying about it, I'll tell you the answer is E, and here's why. It's saying which of the following reactions do not proceed significantly to the right. So it basically means which of those reactions don't favor the forward direction. Okay, and actually all of them, A, B, C, and D, they all are reactions that go in the forward direction. Like A is a strong acid and a strong base. So of course it's going to go in the forward direction. B is an acid with a strong base. So it's like a mice table. It's going to go to completion. C is complex ion formation. Okay, copper ions are basically interacting with ammonia. Okay, and I told you that when you make complex ions, it's favorable, so it's going to go in the forward direction. D is a strong acid dissociating, which you know happens 100%, so it's going to go in the forward direction to completion. E is the odd man out because it's HSO4 minus. Why would it want to gain an H and remake the strong acid? That reaction does not want to happen. It wants to go in the backward reaction. So that's the quick for that one. Okay, but yeah, you won't see that one tomorrow. Okay. Okay, I'm looking through the list here. Let's see, someone asked to go over C, IV on page 21. Okay, I will tell you for C, on page 21, the answer comes out to about like 26.7 milliliters or something like that. And I'll say, like, I know my 6-well personally, we had a lot of short wells. We didn't take the time to go over it. It's okay. Like, I don't think you're going to see that level of difficulty there. Okay. I will say that for that one, you're really just solving the case. It's kind of like the one we just went over where one of the numbers in the KSP expression are set. And you have to solve for the other one. So for this one, it was lead, okay, and iodine. Okay, 2 of them. And guess what? The lead was set because we had that big graduated cylinder. Okay, and it was set to 0.010 molar. Okay, because the concentration of lead in that huge 2,000 milliliters in that container wasn't going to change, kind of set in stone. So you had to solve for what the iodine would have to be to make a saturated solution. Okay, so that's what you're solving. Okay, KSP was given, I forget what it is, 8.7 times 10 to the -9th. Okay, so you guys, this was set in stone. You're solving for the I minus. So you could solve for that. Okay, and that was pretty easy to do. And then it was just a matter of saying that, gosh, if you take that one drop, okay, and the one drop in the problem was described as being 0.05 milliliters, and the potassium iodide that was added, it was 0.5 molar. Folks, I'm just pulling this from the original problem, no surprises there. So basically the question is saying, okay, if the iodine got diluted to whatever that number was that you calculated to make a saturated solution, then what would the new volume be? That's what you're solving for. And it comes out to about 27 mils. So that means that one drop, okay, once it got diluted to 27 mils, okay, any volume past like 27 mils, Q would be less than K, and that's why the precipitate disappeared. Okay, so it was just a Q problem. Okay, so I'll just leave it at that. It's a great problem. If you figured it out, great. You probably won't see something that hard tomorrow, but hopefully it seems a little simpler now. Okay, so what else do we got? Oh, somebody asked, what is selective precipitation? Guess what? Yeah, it was on page 1. It was a term. Okay, selective precipitation. You guys have seen that. It just means like, you know, if you have some kind of beaker with a bunch of ions, like, will one thing precipitate out before another? So actually, just a minute ago, when we were looking at number 4 on page 23, that was kind of like selective precipitation. Okay, because, you know, you basically had this mixture of all these ions like floating around in solution. Forgot what else was in there. Br minus. Yep. So you had all these ions floating around in solution, and then you added lead. Okay, and guess what? The lead would selectively precipitate out one precipitate at a time. So as it turns out, when the lead hooked up with the sulfate, okay, like that was the first one to precipitate out. So then you had all this lead sulfate. Okay, and if you wanted to, you could like stop and you could filter the lead sulfate. Okay, and then the sulfate would be gone. So you've like effectively, it's like separating mixture. Then you could keep adding lead, and you know what? These would all sort of precipitate out in turn, okay, depending on their KSP value and just, you know, how the math worked out. So that's what selective precipitation is. It's just precipitating out, select like thoughtfully one precipitate at a time. You guys had another no calc practice. I think, boy, it was like it had a yellow precipitate and a white precipitate. You guys might remember that. I think it was like number 5. Okay, like that was also selective precipitation. Okay, because the yellow precipitate came out first, and then I think the white one came out second. So that was like selective precipitation. Okay, so that's all you need to know about that. Okay. Says, what is a practice you think that would be helpful in the no calc? Honestly, you guys, if you know, at this point, no, I just want you to get a good night's rest. Like tomorrow's assessment, as is true with all multiple choices, is just a lot of reading, a lot of tricky questions. You got to read it carefully. I actually thought the AP free response question was pretty good. So page 23, 24 obviously had some good questions. We've gone through quite a few. But on page, you know, if you wanted something relatively quick to do, on page 27, it's a pretty good question. AP free response, it had some Q in there, and it had some factors that affect solubility. You know, it had some decisions like when do you double the concentration, or when ions come from the same source, ions come from different sources. So that's maybe a suggestion I have. But most important is just to make sure you rest. Okay, get a good night's rest. And then last one, number 7 from page 23. It says, which of the following's molar solubility will not be affected by pH of solution? So I love that one. You're basically looking for the one that, well, it's actually kind of an interesting question. You're looking for the one that basically doesn't have a conjugate base from a weak acid, but some of them are soluble anyway. So let's see. So of course, sodium phosphate has phosphate, conjugate base for weak acid. Letter B is sodium fluoride. Fluoride is a conjugate base for a weak acid. C, potassium nitrate. Nitrate comes from, of course, a strong acid. So that's a conjugate base from a strong acid. So that one is just going to be equally soluble in low pH or normal water. Okay, so that's your best answer, because C is definitely a conjugate base for a strong acid. I can scribble out. So D, oh, okay. So D, it said, which of the following? Now, you might have said, well, what about, you know, aluminum chloride? Because Cl is a conjugate base of a strong acid as well. It comes from HCl. So low pH, aluminum chloride is not going to be affected by and I wrote PD. Aluminum chloride is not going to be, whoops, let me try one more time, is not going to be affected by low pH, okay, meaning H plus isn't going to do anything to aluminum chloride. But the funny thing about that one, and this is pretty tricky, I admit, is aluminum does make complex ion formation with OH minus. Okay, so if you put a bunch of if you raise the pH, it just said which one would be affected by pH. It doesn't say like acidic conditions or basic conditions. So if you actually make a really high pH, you would make this complex ion. Okay, and that being said, that's going to mess with the solubility. Okay, so that's why D is not the best answer. Okay, it wouldn't be affected by low pH, but it would be affected by high pH. Okay, it would in fact be more soluble. And then E's out, that's also got a conjugate base of a weak acid. So if you were wondering about aluminum chloride, that's the story. It's kind of tricky. Okay, so if you narrowed it down to C and D, then you definitely narrowed it down to the two best choices. Okay. All right. Question 7. Okay, I just went over question 7 from page 23. Okay, so if someone had a specific question about that one, okay, let me know. But like, let me actually, I'm not the biggest fan of that question, but going back just to be more clear about number 7, you probably narrowed it down between C, this is actually choice C, and this is choice D. And you were like, they probably seem pretty similar because they both have conjugate bases of strong acids. So they should not be affected by low pH. But as we said, D has this little trick that it does complex ion formation with hydroxide. So in high pH, okay, it's going to make this complex ion, which will increase its solubility. Okay, and C is not going to do anything like that. Okay, hey guys, the only thing, that's it. I just wish you guys luck, and I hope I answered your questions. I'm checking one more time to see if there's anything else in the chat. All right. All right, well, you guys have a great night. I'll stick around for a little bit. Okay, but I think that concludes our little session for today. You guys have a great night. Let's see.